Okay, let's start with the calibration curve. So you weighed out some amount of the iron sulfate complex, and you did some chemistry to turn it to iron bippy, which we'll talk about in a minute. And here's the molecular weight of the starting material. So what we need to do is figure out what dilutions we made, what their concentrations are, and what their absorbance is to make the calibration curve. So first things first, we'll probably want to know how many moles of this material did we add. So I'll put this down here, change that to moles. So how many moles of this material do we have? And of course, it's simply the grams divided by the molecular weight. And that gives us 6.6 times 10 to the fourth. Now, we then put this into the primary stock. So how large was that? So how many mils was that volume of the primary? Well, we put that into 100 mils, right? And so now we're kind of interested in what the molarity of that primary stock was. And that's not too hard to calculate, right? It's simply going to be the moles divided by the volume, but the volume's in mils, so we need to change that to liters, so we'll divide by 1,000. And we get the primary stock was 6.6 times 10 to the third molar. Okay, so from here, we then took this and we put it in some sort of alquat. We took an alquat, a sampling of it. We took 2 mils, right? So those 2 mils that we took out, we want to know how many moles were moving from that primary to the secondary. So how many moles were in that alquat, right? And that's simply going to be the concentration times the volume, but remember the volume has to be in liters, so we'll change that to liters again. And we get the number of moles that's transferred is roughly 1.3 times 10 to the minus fifth. Okay, so what was the size of that secondary stock? That size, oh, there we go. That size was 50 mils, right? And so we really want to know what the molarity is now of the secondary stock, because that's where our information is going to come from. And of course, our molarity of the secondary stock is simply the number of moles divided by the volume, which is 50 mils, which we have to once again make into liters. And we get the molarity of our secondary stock is roughly 2.6 times 10 to the minus fourth. Okay, cool. So now we made these dilutions with these measurements, right? So we need to know the total volume of each one of our samples, right? We're going to want those in milliliters. And so our total is pretty easy to calculate. It's basically the iron bippy solution that you added plus the extra water. In this case, the manual asks for 7.5 mils. However, you put in what you actually measured in order to get the correct amount. Okay. And so now we're curious how many moles of that iron bippy solution made it into that compound, right? So the number of moles is going to be, of course, once again, the secondary stock concentration, which we'll fix within dollar signs, right? And that is simply multiplied by the volume we put in, which is here. But once again, those have to be put into liters. And we'll see that we put in a variety of concentrations. Copy, paste. So from 2.25 times 10 to the minus 7th down to, or up to 1.39 times 10 to the minus 6. That's our molarity for those. Those are the number of moles, actually, I should say. Not moles, it's not the molarity, it's the moles of those compounds. And then, of course, we're going to want to know the molarity or the concentration of the iron bippy in those. Molarity. Okay, make it small. So we want to know the concentration of the iron BiPi, and that concentration, once again, is simply the number of moles divided by the total volume, which we have to make into liters. And you'll see we have a range of concentrations from 3.0 times 10 to the minus fifth up to 1.8 times 10 to the minus fourth. Cool. So now we have our concentrations of BiPi in the 5 dilutions we made. Now we took some atomic absorption, and we need to find out what the absorbance is. So the absorbance for each of these is simply the minus log of the percent T. But remember, percent T is really 0.79 because we've multiplied it by 100. So we have to divide each one of these by 100 in order to get our absorbance. So there we go. There's our absorbance for our system. And now we're going to want to plot this. So our Y data will be the absorbance. Scatter plot. Select data. Edit. Our Y data will be the concentrations. And then we need to appropriately label this, right? So concentration of iron BiPi, that's in molar. And then over here, I have absorbance at 520 nanometers, and those are arbitrary units. Beautiful. Now we need to add our trend line. Trend line. Come on, drag over. There we go. Bigger. Okay, so now we have our trend line, so we can put the data points on this trend line and then figure out what those, if we have an absorbance, we can figure out their concentration. Now, here's a kind of a pain, right? We have 1, 2, 3, 4, 5 sig figs there, but only 2 in this. So there is a way to get more information from this to really get the full slope and the full intercept, and that's to use 2 different functions. So the first one, of course, to determine the slope would be the function of slope. And we're going to take our known y's, which is the absorbance, our known x, which is the concentration. Oops. I apparently overwrote that. There. And so now you can see we have more decimal places, more significant figures in our slope. The same we can do with our intercept. Once again, just known y's, comma, known x's. And now we're no longer truncated to 2 significant figures. We actually have more, which is minus 0.0639045.